Hello everyone. Today we'll be learning about the mass variation with velocity. Let us consider again two inertial frames S and S dash such that S dash is moving with constant velocity v in positive x direction. Let us consider a hypothetical case of a collision of two exactly similar balls. By similar I mean they have exactly equal masses m. Similar balls A and B moving in opposite direction along x-axis with equal speed u dash in frame s dash. So you can see in the diagram here the masses A and B are colliding. They have the equal and opposite speeds u dash with respect to the frame s dash. After collision, they coalesce into one body, they combine into one body. After collision, the coalesced mass must be at rest with respect to frame S dash. So after collision, the mass seems to be at rest with respect to the frame S dash. Hence, it moves with velocity v with respect to frame S. Now let u1 and u2 be the velocities and masses m1 and m2 be the masses of balls A and B respectively with respect to an observer in frame S. Now using the law of addition of velocities, the above velocities u1 and u2 can be written as u dash plus v by 1 plus u dash v by c square. If you remember, we learned about the velocity addition theorem. So straight away we are importing those results here and we are writing the velocity measurements u1 and u2 with respect to the velocity measurements of an observer in S dash frame. So these are the velocities u dash and minus u dash. So here you write u2 is equal to minus u dash plus v by 1 minus u dash by v u dash v by c square. That is equation number 1. Now it is very important to understand that law of conservation of momentum holds good here also, and so we apply the law of conservation of momentum on the collision of balls with respect to frame S. So we get m1 u1 plus m2 u2 is equal to m1 plus m2 times v. Now these are the initial masses which were before the collision. So the linear momentum before the collision on the left hand side, this value is equal to the linear momentum after collision, which is m1 plus m2, that is the final mass once the balls A and B collide, that is your m1 plus m2, and that mass seems to be moving with the velocity v with respect to the frame S. Now we substitute for u1 and u2 from the equation number 1. So we get this equation here. Now we rearrange this equation, which becomes m1. I go to the last equation directly, which becomes m1 times u dash minus u dash v square by c square by 1 plus u dash v by c square equal to m2 times u dash minus u dash v square by c square by 1 minus u dash v by c square, which implies, please see here how we have rearranged. We want to get the factor m1 by m2 on the left hand side. That is the whole idea. And on the right hand side, we are left with, because you see here the numerator on both the sides gets cancelled, which is u dash minus u dash v square by c square. So on the right hand side, I have left with 1 plus u dash v by c square by 1 minus u dash v by c square. Now on the right hand side, the format is little complicated to us, so we want to simplify this. Moreover, if you see m1 and m2 are the masses which were measured with respect to the frame S or the observer O with respect to the frame S on the left hand side, and on the right hand side you have the primed quantities which are with respect to S dash frame. So we want to get the measurements with respect to the same observer on both sides. So on the right hand side also, we want the velocities u1 and u2, not u dash. So in order to do that, we can read here equation 3 shows a relationship between masses of balls with respect to S, and their velocities with respect to s dash frame. Now to obtain the relation between masses of balls and their velocities with respect to frame S, that means we want relation between m1, m2 and u1, u2. So we have to consider some quantities, say, which is 1 minus u1 square by c square. This you will have to assume. We want to get this factor, and we'll see how it simplifies our job. So I just substitute for u1 from the previous velocity addition theorem, and I get this equation here. And you can open it up properly. You can open it up, and you see here we are left with the equation number 4. It takes a bit of time to open it up and then rearrange all the equations, and you see it comes out in a very familiar form, which is 1 minus v square by c square times 1 minus u dash square by c square by 1 plus u dash v by c square whole square. So similarly, if you have 1 minus u1 square by c square to be equal to this, then we can also show that 1 minus u2 square by c square will be equal to 1 minus v square by c square times 1 minus u dash square by c square by 1 minus u dash v by c square to the power 2. Now this equation number 5, you can either calculate exactly in the same fashion as we have done the 1 minus u1 square by c square, or you can just remember the result. That numerator will be same for both equation number 4 and 5, only the denominator has changed. So as you see, what we are trying to do here, we have equation number 4 and 5 with us now. So we divide equation number 5 by equation number 4, and we take the square root on both sides. We get root of 1 minus u2 square by c square by root of 1 minus u1 square by c square, which is equal to 1 plus u dash v by c square by 1 minus u dash v by c square. So you see, equation number 6 is what we needed to substitute for this particular right hand side factor in the earlier equation. So we compare equation number 3 with equation number 6. So we get our m1 by n2 to be equal to root of 1 minus u2 square by c square by root of 1 minus u1 square by c square. It is a very familiar format, but still it has to be reduced further to be able to make more sense to us. So suppose M2 is at rest. Let us suppose M2 is at rest with respect to frame S. Then U2 is equal to 0 because M2 is at rest. And M2 is equal to M0. We assume M2 to be equal to M0, where M0 is the rest mass of the ball B. Because we already said that these are identical masses, if you remember. So let us say M0 is equal to M2, where M0 is the rest mass of the ball B. Then the equation 7 becomes M1 by M2 is equal to 1 by root of 1 minus U1 square by C square. So it has simplified now. Now as both the balls are similar, hence the rest masses of both the balls are same too. So the rest mass of M2 is equal to the rest mass of M1, that is equal to M0. Hence M1 by M0 is equal to 1 by root of 1 minus U1 square by C square, which implies M1 is equal to M0 by root of 1 minus U1 square by C square. Now here M1 is the mass of ball A, where when it is moving with velocity u1 with respect to frame S. After collision, the coalescent mass containing mass of ball A moves with velocity v with respect to S frame. So please pay attention here. After the collision, the coalescent mass containing mass of ball A moves with velocity v. So that is what we have discussed earlier also. And hence you can replace straight away the velocity u1 to be v. And then in general, if we take the mass of ball A as m, so I get m1 is equal to m here. So I have the relativistic formula for variation of mass with velocity, which is equal to m is equal to m0 by root of 1 minus v square by c square, where m0 is the rest mass of the body and m is the effective mass. So this is a very, very, very important relation, and you see m becomes greater than equal to m naught as the velocity approaches the speed of light. Thank you for the attention.